Hey, we are going to now talk about accuracy in design and manufacture. This is making sure that we understand how things are checked for quality, essentially. You'll have heard of things like quality control and quality assurance, but now we're looking at the specific ways in which that can be done. So on this slide here, what you can do is just put on a load of images of different tools that we have for being more accurate. So, I mean, some names that we have that we can talk about here are, starting with the basics, we've got steel rulers, and we've got tri-squares for marking out, and that's if you're doing sort of like hand making stuff. You also have a marking gauge which you can use for woods as well. Okay, and then we then have other things as well. So if we're getting more, that's sort of, I guess, yeah, we can visualize it like this. This is sort of like level one of accuracy. So it's sort of limited level. Level two, this is where you'd have things like your calipers. You'd have touch probes. Actually, no, that's the next level up. Yeah, you'd have. Hmm. I guess on certain machines, actually, they've got quite good ways of checking for accuracy. So, on say if you're on the lathe, on the center lathe, you'd have the dials on the center lathe, and you'd have yeah, you'd have the digital um, digital gauge as well, which is the one that's the one which looks a little bit like a sort of letter C, and it's got the little probe that comes out like that, and then you've got the collar that comes off here, and then this one is the one that gives the same level of pressure each time. Okay, sometimes the digital gauge, that's if it's got like a screen on it, or it's called yeah, or micro gauge. Sometimes they go by a few names. Okay, then I guess level three up from there is this is where we're getting into more like sort of using lasers, ultrasound, infrared. Um, I guess, I mean, you might even be, yeah, looking at touch probes as well. Touch probes, so the CNC machine can actually check that the dimensions are correct. So I just remember the actual, I was having a mind blank there. This is just called a micrometer. That's another name for it because it measures in micrometers. Yeah, okay, so yeah, I mean, touch probes, all these ones here can be built into processes like CNC milling, and they're predominantly used for metals because it's only really metals where you can work to such levels of precision. Things like plastics and woods, they're too affected by other things around them. So it's only really metals which can actually get to levels where you need to use things like this. So that's the tools for accuracy. So you can just get images of those to put on there. Um, yeah, in terms of yeah, we've talked actually already a little bit about some of these areas, so I can just sort of go on and enhance them. Another one we just need to talk about here is jigs. So jigs are a way of just ensuring repeatability. Now, this might mean if you had, say, if you got a pillar drill and you're wanting to drill a hole in exactly the same place on a piece of material every time, it could be as simple as having a little bracket set up clamped onto the pillar drill machine. So it could be, yeah, that's like sort of screwed onto a bed. We do this with CNCing as well to make sure that the material always lands in the same place. And then inside there, you just push up your billet of material right into the corner, into that corner there. And then that means that the drill will always come down and drill in the same place every time. So you can then take this one out and then put a new one in, and it would drill in exactly the same place. And then each time you're not having to mark out and measure and make sure it's always in the right place. So sometimes if you've got a batch of items to do, making a jig can save you actually a huge amount of time. So it ensures repeatability, it's more accurate, and it's also a lot faster. Yeah, so jigs, and I mean, even sometimes with jigs, if you're, say, welding two pieces of metal together, say if looking from a plan view here, if we've got two bits of square tube and you're wanting to weld like one against another one, but you want to get it in exactly the right place each time. So once you've done one and then you do the other one, you want to make sure that it's always in like the same line. Now, what you typically do in this instance is you'd actually have a jig that might be magnetic, and then that's something like that. So you'd slide the piece of metal in against the vertical piece like that, and it would be held in place securely. And then that would be another sort of magnet piece there as well. And then that would hold it in place. And then when you actually then do your weld bead, you fill up that area there with welds, it's always in the same place every time. So that's kind of how jigs can be used. So looking at the keywords we've got here, then there's a few we need to know. Now I think accuracy and tolerancing, we mentioned already that high level of this equals higher cost because it takes longer. And when you're needing higher accuracy as well, you're also needing more specialist equipment. Often things that are not found in conventional workshops. Yeah, measurements. I mean, this is really where we're talking here, like steel rules and calipers and things like that, steel rulers. Yeah. The one on here that you might find a bit odd is datum. Now, datum it's like a reference point. If we're looking at a plan view of a piece of material that we're going to drill a hole in, okay, there's a piece of MDF, and we're going to drill, say, 2 holes there and there. And this is our technical drawing that we're looking at. So these would have what we call center marks on them, like that. Now with circles or holes, they must have center marks applied to them, because that's how we know we're going to drill it in the right place. So here's what you'd have on the drawing. You'd have dimensions, which would go from here, and that's what we call the datum point. The datum point is the point at which all dimensions start. It's almost like the zero point. Okay, so starting from the 0 point, we go horizontally across the x-axis first, so we find the first feature, and that's the center mark there. So I then get my little arrows and I'd write in there 10 mil, for example. That's the first dimension. Now the second hole, the tricky thing with this is knowing, where do we actually take the dimension from? Do we take it from here? Or do we take it from here, from the datum? The answer is this. If you take the second dimension from here, say that's 20 millimeters. Okay, now talking about tolerancing. It's very hard if you're doing things, especially by hand, to be absolutely accurate. Now let's say that you actually drilled this hole was actually kind of more like 10.5. So let's say we were actually pretty out on the tolerancing there. We went over the dimension. Now what would happen is the 20 mil hole would also be too far along from the datum. So this would, if that happened to the blue dimension, the green one would then become 20.5 as well, because it would be too far away. Sorry, in fact, no, it wouldn't. If we were using the reference from the datum, but we measured from there, then this would then be 20.5 millimeters. So that would be too That would then be too long. It'd be in the wrong place. So that'd be a failure condition, both of those there. So let's look at the proper way of doing it. We seldom do this kind of dimensioning strategy here, actually. We call this method actually chaining. We have one dimension, then affects the next one, then affects the next one, then affects the next one. The reason is there's too much room for error. Each dimension affects the other one. So if one's out, all of them come down. So it's much safer to always go back to the datum point. So I'm going to erase these bits here. So yes, much safer is to do this. I'm going to get my green pen and we go from the datum point and we go out to the next marker. So then this might be, say, 30 mm. Because now if this is 10.5, it doesn't matter because the second hole is still in the right place. So that's where datum dimensioning comes in really important. And we can put out the next one out over here. I've just done my writing in the way. And say this might be also 10 mil. Like that there. And then for the diameter of the hole, we'd mark that like this, a little hole each side, sorry, arrow each side, and then we'd have the diameter symbol and we'd say we call that 5 mm. If you were doing a radius marker, you'd have something like that instead, just a little arrow there from the center, and then that'd be R2.5 mm instead. And that's a very crude, very crude drawing, but it shows you the principles of datum points. Okay, the last keywords on there we've talked about. Jigs we've already done. Fixtures is the same as the jig, really. It's just clamping something, or the same as the welding. It's the same as it's the same as really using a jig. And then a template is kind of like if you were drawing out, or say if you had a pretty complex pattern that you were trying to mark out on some, I don't know, like some acrylic that you were going to cut by hand or something. Let's say you had a pattern that was kind of pretty complicated, like a sort of S shape like that, and maybe it's going to be part of a hinge for something like that, and you need to cut it out of a piece of acrylic that's underneath like that. Now, to get this shape drawn accurately onto the acrylic, if you're cutting it by hand, it would be too difficult to use measuring tools to do that. So much simpler would be to either laser cut that or print it on paper. So you print on paper or card, cut out, and then trace onto the material. And that ensures that you get the same shape each time. Okay, the grinding, precision grinding, we talked about it in class, but this is a way of getting absolute, this obtains absolute dimensions. And also can get exact surface finishes as well. I remember at university being blown away by once you'd surface grinded 2 pieces of steel to exact dimensions, you could actually just use force and rub them together. And because the surfaces are so flat, it actually creates a vacuum, and then the 2 pieces just hold themselves together. Okay, and that's it for there, guys. So you can then have a go at the exam pro questions. Well done.